Meanwhile, a race car driver is recovering from a horrible accident at Texas Motor Speedway. Check out this video. Drivers are traveling about 200 miles per hour in the Chevy 500 when Kenny Rack's car crashed into another car. He was sent airborne before crashing into a steel guardrail. Pieces of that car scattered across more than a quarter mile of track. Rack suffered extensive injuries. He's listed in serious but stable condition. He had surgery last night for a broken thigh and ankles. He faces more operations for a broken lower back and a broken sternum. The other driver, amazingly, was not hurt.
It says a lot about the construction of these cars and the kind of medical care they get at the track immediately after.
All right, so what about the construction of these cars? They make these cars extremely fragile, guys. Why do they make them so fragile? I mean, I would hate to drive one of these because if you get rear-ended, the car is going to explode. All right?
So they absorb all the energy so that you don't have to.
Okay, very good. I like that. In order to take the energy away from the driver, right? All right, so give yourself 5 points for that one. So the question is, what's energy? How do you transfer it? How do you absorb it? Okay, once again, guys, you're supposed to know this stuff from somewhere. Okay, so this is a fast review of what I need before we start the next chapter. All right, so energy is an abstract concept. Abstract doesn't mean it's complicated. It simply means it's a step removed from life, basically. All right, you kind of have to dig in order to get to it. Newton did not discover it, despite the fact that he was dancing around the concept for a while. And physicists came up with this concept during the 18th, 19th century for thermodynamics. That's what happened.
Yeah, according
It's a really, really powerful concept.
to plan, as they leapt off the bridge while tethered to the cable. The team was about to reach the end of their first arc. The cable snapped, and 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside, helmet cam, Kenny, myself, boy, sorry. She does the front flip. Here we come, going into full velocity right here. Probably reach about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't the seat just disconnect? My arm goes out, and here we come to the water. Pow! Oh, a ton of wrecks. Look at this price at 40 feet. The action though.
Yeah, according to
It's
plan.
awesome,
Right
actually.
here. Probably reach about 78 miles an hour, right about here, 78 miles an hour.
78 miles per hour this way. How did they know they were going to go at 78 miles per hour?
You'll see the harness disconnect from the cable right there. Didn't the seat just disconnect? My arm goes out, and here we come to the water. Pow!
And splashdown, it's 91 miles per hour. How do I know that's going to be 91 miles per hour?
While tethered to the cable. As the team was about to reach the end of their first arc,
What if these guys decided to jump directly into water, all 5? How fast do you think they would be moving at the time of impact with the water down below? Do you think they would be going faster, slower, or about the same speed as 91 miles per hour?
cable snapped.
My arm goes out, and here we come to the water.
Believe it or not, these 5 end up surviving this impact at 91 miles per hour. 4 of them had broken bones. 2 of them ended up fracturing their necks. But this was survivable. So my question is, if they were to jump directly into water, do you think they still would have survived? Yes or no? What do you guys? Okay, who say no? Lucas? You say no. Okay. Do you think they would be going faster, slower, or about the same speed?
About the same.
Okay, Lucas, you're thinking they're moving about the same speed? Why?
Well, because the speed of which an object falls is independent of its weight, so they're still going to be falling with the same speed, even though they're connected to the rope. But the rope absorbs some of that energy that they would have imparted on the water. But without that rope, they would have hit with a much larger impact or a lot more energy and make a really unpleasant.
Okay,
really
so what you're
unpleasant
saying is
collision.
without the rope, they're falling unimpeded, right? So they would be hitting the water faster, right? At a faster speed.
Yes.
That's what you're saying. All right, I think most of you guys would agree with that. So let's move forward before we will circle back to it. All right, so Galileo's famous incline experiment. So he's rolling the ball down, and the ball is going back up to the same height. Galileo was trying to figure out the gravitational acceleration. So when you drop something, obviously it accelerates fairly fast, so you can't see the details. But when you put the ball on an incline, you can slow it down, and you can measure the distances and times. And that's what he was doing. So that's how he discovered the concept of inertia. So the question is, why does the ball keep going back up to the same height if you ignore friction? All right, so let's get back to the definitions, basic definition. So energy is the capacity to do work. So if you have energy, you should be able to do work with it. And what happens when you do work? You transfer that energy. All right, so work is a process of transferring energy. So energy is the capacity to do work, and work is a process of transferring energy. All right, so now when you do work, you transfer energy, but the question is, what's considered work? What's considered work is a force causing displacement. So there has to be an applied force, and that force has to be responsible for this displacement. All right, so there's applied force on the car, and because of the applied force, the car is getting displaced in the forward direction. So the work is being done on the car. What that means is the energy is being transferred to the car. All right, as you all know, the energy, the proper unit is going to be joules. In the United States, we use calories, kcal, kilocalorie. 1,000 calories is going to be 4,186 joules at your examples of energy and work is all over the place.
Of this clip. Let's go.
All right, so he's getting dragged. Is there work being done on it? Of course. There's an applied force, and he's moving along the direction of the applied force. What that means is the energy is being transferred to him. All right, so we're good with that. All right, is he doing any work on the crate? Notice that this guy is applying a force on the crate, but the displacement is 0. So there's no work is being done, which means that no energy is being transferred to the crate. In this case, applied force is acting on him. Notice that he's getting displaced along the direction of the applied force, so which means that the work is being done on him, which means that the energy is being transferred to him. All right, what's the best answer for this one and why? Let's record in the computer sound.
A.
Okay, you have to go between A and D, right? The only one that makes sense is A. All right, so there's not going to be work unless there's motion or movement. So the force has to be responsible for motion. Right? Speaking of force, the force is going to be responsible for the work itself, which means that the force needs to have a component along the direction of motion. All right, so this force is responsible for that motion because the force is a component along the direction of motion. That's what we're interested in. Okay, so if force and displacement, if they're in the same direction, it's known as positive work, which means that the energy is being transferred to the object that you're pushing on. In this case, you're lifting the cat up, which means that the cat is being energized, which means that the energy is being transferred to the cat. Now, you're carrying the cat forward at a constant speed in a straight line. If that's the case, the force that you're applying, applied force, is there to balance the weight of the cat. And notice that this force is 90 degrees to the motion, which means that this force is not contributing to motion. So what that means is that no energy is being transferred to the cat. In this case, we're putting down the cat. Applied force is in the opposite direction of the displacement. All right. If the force is in the opposite direction of the displacement, the work is negative, which means that the energy is being taken away from the cat. So, which means that the cat is losing energy. All right. So whenever you lift something up, lifting is positive work. All right. So lifting is positive work. So the weight set is being energized. And you pull it down, the work is negative. So the energy is taken away from it.
You know what they say? No pain, no brain.
All right. So this is positive work, which means that the energy is transferred to the weights. Okay, so what that means is this thing is energized. So the energy means the capacity to do work. What that means is if you're not careful, you can actually apply a force on it and make you move along the direction of the force. So this was a really nice illustration of
Remember, it's
how the energy gets transferred.
with your legs, collapse with your spine.
Positive work, so the energy is transferred to the object that he was lifting. So this thing is energized. When this thing is energized, that means it's got the capacity to do work. So if you're not careful, it and it can make you move along the direction of the force. All right, do you guys notice that both these guys have the same technique, more or less? They must have the same trainer. These guys compete like the Canadian national team. You can tell that they got free healthcare, so they're very frivolous in their attempt. All right, so does gravity extend all the way out to the moon? Of course it does. If it didn't, what would happen? Moon would have gone in a straight line at a constant speed, right? So here's a question for you: how much energy is being transferred to the moon by the Earth, by the force of gravity? What is the amount of energy being transferred to the moon by the force of gravity? Any ideas? All right, so gravity extends all the way out to the moon, and how much energy is being transferred to the moon by the force of gravity?
A lot.
All right, Caleb says a lot. But how much? Like 2 scoops of ice cream or something? Is it Diet Coke or regular Coke? It's about 3. How much energy is being transferred to the moon? What's the amount of work being done on the moon by gravity? That's what it means. Okay, guys, you have to get back to the conditions. A lot of physics is done conceptually, and then you do the problems. Real physics, we don't really do. The mathematics is the last thing you do normally. All right, you have to do problem solving in your head. What is the definition for work? Work is an applied force having displacement, right? So which means that the applied force needs to have a component along the direction of motion. So what is the components of the applied force along the direction of motion, given the fact that this is 90 degrees of motion itself? It's none. So no work is being done on the moon. No energy. So what that means is no energy is being transferred to the moon. All right, because the force is 90 degrees, the motion energy is being transferred, and that's it. All right. Okay, I'm gonna skip that one. Only one in the position of that. So work is a process of transfer energy, which means that whenever you do work, you transfer energy. So whenever you lift something up, what are you doing? You're applying a force on it. It's getting displaced along the direction of the force whenever you lift something up, which means that the energy gets transferred to it. So the amount of energy that you transfer to an object by lifting it up is going to be stored in that object. What that means is that the object is energized. So the amount of work that you do in lifting something up against gravity, and that's an important distinction, as you will find out shortly, is the amount of energy that gets stored in an object. So this is known as the gravitational potential energy. All right. So gravitational potential energy is the amount of work that you do against gravity in lifting something up, and that's also the amount of energy that's going to get stored in that object.